Hi, my name is Nikhil Raghav. I'm a doctoral student working jointly at the Institute for Advancing Intelligence at TCG and Department of Computer Science at RKM, India. This work is accepted at ICASSP 2025, and in this we propose a variant of the spectral clustering technique for the task of speaker diarization, which is computationally efficient compared to the existing auto tuning approaches. This work is in collaboration with Dr. Abhishek Gupta, Dr. Ambi Saidullah, and Professor Swagatam Das. First, we'll try to quickly understand what is speaker diarization. So it can be understood as given an audio recording that contain multiple speakers. The diarization system tried to predict at what point of time this speaker is speaking. So it tries to address the question of who spoke when during the given conversation. Speaker diarization has applications in day-to-day life, ranging from a doctor-patient interaction, courtroom proceedings, to scenarios like collaborative learning for children. Also, in everyday meeting interaction, it can help in meeting summarization as well as it can help in some analysis. Other interesting applications include forensics, and cocktail party problem is one of the most classical problem in this domain, in which speakers are in a party where there is some background music and you try to identify at what point of time he is speaking. So this kind of scenario becomes very challenging. There are some factors which make this process challenging. For instance, quantify the number of speakers that are in the recording is a very big challenge. And it's more likely with the increase in the number of speakers, they plan to overlap each other. So the presence of overlapping speech, how to handle the overlapping speech is a crucial factor in the performance of the system. And when we have uneven distribution of speech across the speakers, so while doing the clustering, it can also tend to produce more errors when it is unevenly distributed. Then there are some variations which comes into the play. Some variations are intrinsic. For instance, the different speakers have different kind of emotion, different kind of accent, different dialects, when they often come from different nationality, different mood, different like, gender. So all these factors bring some variability in the recording. There are some factors that are extrinsic, like the kind of microphone setup, for instance, that we used to record this recording, uh, like closed talk collar microphone versus a far field array microphone can bring in variations in the audio that is being generated using these devices. And the scenario in which you record also makes diarization very challenging. For instance, in a like a meeting kind of domain, which is a very closed environment, like a closed talking environment where there's no presence of background noise compared to a domain like restaurant where there is very much disturbance in the background. So these all factors bring some additive challenge to which makes this process difficult. Let's first look at the pipeline, how the flow of the diarization is, how the pipeline works. So the model pipeline begins with which takes a raw input audio as the waveform as the input to the system. Then some pre-processing techniques are often being employed in the form of speech enhancement to improve the overall quality of the speech. And if you observe, like in the audio, only the speech regions are somewhat like useful for our tasks. So speech activity detection or SAD is being applied to identify the speech regions and non-speech regions are being removed. And on these speech regions, segmentation is being carried out. Uh, Conventionally, it's being homogeneous segmentation, where you form a segment of fixed length, for instance, say 3 seconds, and for each of these segments in the entire audio, you try to obtain a speaker embedding representation, which is a vector of fixed dimension that is often being extracted using some pre-trained uh, pre-trained deep learning model. And once you have all those embeddings, then a clustering technique is employed to cluster these representations and to obtain the speaker clusters in the audio. Some post processing techniques are often being employed and they are somewhat optional to refine the speaker assignments at the segment boundaries and the system output, the diarization output. So this is just a prototype where I've taken like two speaker case where this blue and orange marks the two distinct speakers in this recording. In the literature, what I observed that enough work has been done on the other module, for instance, SCD and segmentation, although they have some challenges, but this clustering module is somewhat overlooked in aspect of diarization because it is an unsupervised learning problem and it's quite challenging. We'll quickly see in brief the two kind of approaches that I have reviewed, which are still the state of the art in respect of the modular speaker diarization pipeline. One is the conventional spectral clustering or CSC, that is plus like categorizing the semi-supervised because there is some data dependency while tuning the parameters, and the other is unsupervised, that is auto-tuning clustering or ASC, where there is no data dependency. And we'll be going to talk in detail in the coming slides. So first, let's look at some of the limitations which are there in the standard spectral clustering for speaker diarization. So it assumes to prune a fixed number of neighbors in the affinity matrix construction. So this matrix, affinity matrix, is the matrix of similarities where in each row you have a embedding or a node, and for uh, each node you try to show the similarities with respect to the other nodes. Analogously, you can think of it in terms of a graph where all these embeddings are the nodes in the graph, and when you have the entire affinity, like it's full affinity you take, so the graph is fully connected and it's unidirectional. But yeah, these scores can be interpreted as the weight of the connections between these nodes. And you try to solve a graph partition problem where you're interested to identify, say, K-many subgraphs where those form the speaker clusters, still they're connected, and you try to identify those. But this assumption is not somewhat correct when you have an unbalanced distribution of data across the speakers. Then, as I said earlier, that there's data dependency for tuning the parameters. So how can this be automated or generalized to some unseen conditions where data can come from complete scenarios which are wild and to incorporate domain knowledge? So the conventional spectral clustering CSC start with this raw waveform, and once we have these embeddings, you form the similarity matrix, and cosine similarity is the distance matrix that is somewhat suited for the task of speaker diarization. This block pruning is somewhat where the main contribution of this work lies on. Then you have the Laplacian computation. You perform singular value decomposition to have the eigenvectors perform the k-means of the spectral embeddings to have the diarization output. So in this, typically this parameter alpha is being tuned on the development data by, like for each choice of alpha, you prune a smaller n times 1 minus alpha, these floor of this, like that many elements in each row of the affinity matrix. And but this has a data dependency, and that's not good. Then the another approach is autotuning spectral clustering, which is able to get rid with this limitation of data dependency. It works on the idea of normalized maximum eigengap, but still has a limitation that it produces a proxy DER and is computationally expensive. So it's not the ideal choice in real time. So addressing these limitations, first, like in the spectral clustering process, we come up with the creative idea of adaptive neighbors to prune the neighbors adaptively corresponding to each node in the affinity matrix that will tackle the unbalanced distribution of data. There's no data dependency and it's still computationally efficient than the auto-tuning spectral clustering. So that's SC-pNA algorithm that we have proposed. So these are the two important blocks in the flow of the algorithm where our contribution lies. So I'm going to discuss in detail how we form the like two speaker clusters in each row and how we retain the similarity scores. So let's focus on the first block. In each node of the affinity matrix, we identify two clusters using k-mean clustering algorithm, where these clusters CW and CB correspond to the within speaker similarities and between speaker similarities. And this idea of choosing this threshold that is given by ER optimal is motivated from the speaker recognition literature based on F ratio. And this ER optimal is given by this threshold delta, and this ER, like I'm talking about equal error rate, where false acceptance rate and false rejection rate are equal. For this choice of threshold, when we prune the lower similarity scores and put the performance of the system, we identify that it is still good but not very competitive to the state of the art. So we thought of why not only we retain the like only those within similarity score which are ideal for a speaker cluster, a speaker segment. So we retain only the top 2% same speaker similarities, and this idea worked for us in this proposed work. And in terms of complexity, it doesn't require sensitive tuning, and it is still has an order of NQ complexity only due to the gap factor computation, but it's still better than ASC, which has an order of n to the power 4 com complexity. While evaluating the performance of the system, there are some errors that the system will introduce. Like if you compare the human ground truth and the system's prediction, first error is the excuse me false alarm, where non-speech regions recognize the speech, sometimes just miss the speech regions, and produces wrong speaker labels. Our experimental setup looks like this. We use the diehard 3 dataset, which is a very challenging dataset for the task of speaker diarization. It comprises data from 11 diverse domains ranging from meeting to restaurant domains. We use the speech brain open source speech toolkit for our task. We adapted the AmiriCP there present in that toolkit. I'll share the GitHub implementations later on. We use the kappa TD and NP train embedding extractor, which is trained on voxelib dataset for extracting the embeddings, and these are the remaining configuration. And as said earlier, we use the diarization of the rate to measure the performance of the system. How to retain, how to choose that P. Uh, we vary that way in a very wide range from 10 to 15%, and compare the performance of SC-pNA with the like competitive CSC and the auto tuning ASC approach, and we identified the majority of the cases. 20% is a very promising choice where the error rate was either close to CSC or better than ASC. So here there are just 4 cases which are demonstrated that in 3 of the cases you see that ASC is able to beat SCPN is able to beat ASC. These are the results of a system on the diehard 3 dataset, which contain like here this performance is on the evaluation data. And if you see, it's still the proposed one at the bottom right, the last column is the SCPNA, and the first column CSC act as baseline for us, but yeah, we were want to improve over the ASC, and in majority of the cases, the dilatation error rate that CPNA gives us less than ASC, but still, yeah, in some cases like code, for instance, and cast interview, ASC is still better. However, the overall performance of the system is better than ASC for the proposed SCPNA. These are some of the future research directions that we look forward to work on, like how to handle the overlapping speech, because the current diarization system, like the testing algorithm, assumes the presence of only uh, one speaker. That is a hard assignment. So how to handle this, and our implementations are available on this link, and I encourage you to please check. And if you have any queries, feel free to reach out through these emails. So thank you so much, and look forward to have more engaging discussions at the ICASSP. Thank you.